Okay, so today we're going to talk about section 1.8 of the textbook, which is the section on continuity. So this begins with the definition of continuity. So the function f is continuous. F of x is called continuous at the value a. So continuous at a if the following, well, I guess if the following condition is true. That is, if the limit as x goes to a of f of x is equal to f of a. Okay, that's the definition. Okay, so learn that definition. Most importantly is sort of what this implies, what this definition implies. So notice that that f is continuous at a, and I'll write this CTS to mean continuous. We just use the word continuous so much that that we get sick of writing all of those extra letters in between, so we just take CTS. Notice that that f is continuous at a if the following three conditions are true. So the first is that f of a is defined. It has to, right? Because here we're saying f of a in the definition, so f of a must be defined. Two, we need that the limit as x goes to a of f of x exists. Right? That's saying that this limit equals something. And then three, we're saying that not only does it exist, but it equals f of a. So these are the three conditions that are necessary for a function to be continuous at the value of a. One geometric way to think about this, so geometrically, this just boils down to f is continuous at a if you can draw the graph around f of a without lifting your pencil. Okay, so this is a geometric condition for continuity. All right. So f is called f is discontinuous. So discontinuous at a if not. That's just a little bit of notation, so we say discontinuous, or a is a discontinuity. So let's just take a look at a graphical, like a visual example, just to get warmed up here. So here's a graph. I'll draw a function. Maybe I'll be interested in these quantities here. Let's see. Let's go like this. Okay. So here's the graph of a function. And we notice, so where is f not continuous? So f is discontinuous at, let's see, looks to me like it's going to be x equals 1, x equals 3, and x equals 5. Okay, and let's see why. Okay, so here f is not defined. Okay, here f of 1 is not defined, so that's one condition. So it can't possibly be continuous there if it's not even defined there. Here, the limit does not exist. Right? At 3, because the trend coming towards 3 from the left-hand side does not equal the trend coming towards 3 at the right-hand side, so the limit does not exist here. And then here, the limit of f as x goes to 5 is not equal to f of 5. Right? This height right here is f of 5. The limit, whatever the limit of f is that height right there. So in order for our function to be continuous at x equals 5, we would have to have that circle right there. Okay, so these are three instances where the graph tells us immediately that this function is discontinuous at these points here. Okay, let's move on to another example. Well, maybe first a definition. So we'll say f is continuous at a from the right. So this is from the right, continuous at a from the right, if the limit as x goes to a from the right-hand side is equal to f of a. So that's 1. 2, continuous from the left. So continuous at a from the left. And that's if when you approach a from the left-hand side. Get that. And then 3, f is continuous on the interval from a to b. Okay, so here we're going to define continuity on the entire interval if f, let's see, so condition 1, f is continuous at every value between a and b, and then 2, f is continuous from the right at a, and then 3, f is continuous from the left at b. Okay, so your picture here would be of something continuous. Let's say b. There we go. So there's the graph of a function. It's continuous at every value in between a and b, and then, well, we can only approach from the right at a, and we can only approach from the left at b. So this is the definition of continuous on an interval. All right, let's take a look at, we've got a theorem here. Okay. If f of x and g of x are continuous at a, and if c is any constant, then the following functions are also continuous. All right. So if f and g are continuous and c is any number, then the following functions are also continuous at a. Here they are. So we can take f and g and sum them together, or take their difference. We can multiply either the function f or g by the constant c. We can multiply f and g together. We can divide f by g. This last one is as long as g of a is not equal to 0. Just can't divide by 0. So that's a theorem. Another theorem, and these are theorems that I just anticipate that you will use all the time through this course. Another theorem, the following types of functions are continuous on their domain. So polynomials, rational functions, so that as ratios of polynomials. So here's polynomials look like this: x to the 37 plus 2x cubed minus x plus 4. There's an example. Rational functions, 3x squared minus 1 over x squared plus 2. Root functions. Square root of x, cube root of x, etc. And trig functions. Sine of x, cosine of x, tangent, and so on. So let's do an example. On what intervals? On what intervals is the function, let's say f of x is the square root of x plus, let's do x plus 1 over x minus 1, and then minus x plus 1 over x squared plus 1. Okay, so on what intervals is the function, this function f, continuous? So that's our question. Here's the solution to this. Well, this is just a sum or difference of three functions. There's that function, and that function. So we really just have to, this is a root, and these two are rational functions. So we really just have to find what the domains are for each of these in order to determine continuity. So the square root of x has domain, you can plug in any number bigger than or equal to 0 and less than infinity. X plus 1 over x minus 1 has domain all of the real numbers minus the coordinate 1. Okay, maybe you would write this equivalently as minus infinity to 1 union with 1 to infinity. So all real numbers except for 1. Either of these is acceptable. And then x plus 1 over x squared plus 1 has domain all of the real numbers. So, because nothing makes the denominators equal to 0 in this case, so this has domain all real numbers. This second function here in this sum of these functions has this as its domain, and the square root function has domain all non-negative numbers. So to find out where it's continuous, well, this is just a combination of these. So we just have to look at what the intersection of all of these domains are. So we have, okay, so we have the real numbers here. Okay, now to look, we need this domain, so we need to restrict to that, and then we need to make the further restriction to these. So the answer is, well, we're allowed to be between 0 and 1, but we cannot include 1. And then we are allowed to take everything past that. So this is, if you wanted to draw this on the number line, here's 0, here's 1. You would put a giant circle there. You would put a solid circle there. You might indicate everything there, and then you would indicate everything the rest of the way. Okay, but this is the right answer to that. All right, let's look at another example. Let's evaluate the limit as x goes to pi of the function sine of x over 2 plus cosine of x. Okay. Now the thing that we notice is this is a quotient of two functions. It's the quotient of sine of x and 2 plus cosine of x. Okay. So where are these two functions continuous? So this function is continuous on all of the real numbers, and this function is continuous also on all of the real numbers. Okay, so we're taking a quotient, so we're really only concerned about when the denominator of this is equal to 0, but the denominator of this is never equal to 0. 2 plus cosine of x is always positive because cosine of x. So cosine of x is always going to be, let's write this. Cosine of x is always between -1 and 1. So a number that's always between -1 and 1, when you add 2 to it, can never be equal to 0. And so this function, its domain is all of the real numbers. So that means that it is continuous everywhere. So sine of x is continuous everywhere. So that means that the limit as x goes to pi of this function can just be gotten by plugging pi in. And if I know my sines and my cosines, this is equal to 0. Sine of pi is equal to 0. Okay, another theorem. If g of x is continuous at A, and if f of x is continuous at g of A, then the composition function, f composed with g, is continuous at A. So let's look at an example that applies this theorem. Where is sine of x squared plus 1 continuous? Okay. Well, this is a composition of two functions. G, in this case, here's the solution to this. G, in this case, is the function x squared plus 1. F is the function sine of x. And so f composed with g, that's our notation, f composed with g is sine of x squared plus 1. Well, now look, x squared plus 1 is a polynomial, so it is continuous everywhere. And sine is continuous everywhere because it's a trig function. So therefore, we know that if we compose these two functions, we get a function that's continuous everywhere. Since f and g are continuous on all of the real numbers, so is f composed with g. So that's the answer to that question. Where is sine of x plus 1 continuous? Okay. Let's look at a theorem that is has a very common sense statement that relies heavily on continuity. So this is called the intermediate value theorem. For those of you who are listening, the intermediate value theorem will be memorizing this theorem is absolutely essential, and I will ask you on the exam to give the full statement of the intermediate value theorem. So the intermediate value theorem says that suppose f is a continuous function suppose f is continuous on the closed interval from a to b. Okay. Now suppose also that f of a and f of b are not equal to each other. And then so f of a is not equal to f of b, and let n be any number between them. Okay. Then what the intermediate value, so this is all of our this is what we're assuming. These are our assumptions. So then the conclusion of this, then there is a number. This is the conclusion of the theorem. there's a number c, where c is between a and b, strictly between a and b, where f of c is equal to n. Okay, let's take a look at two pictures that illustrate this fact. So here's one picture. There's f of a. And that height right there looks like it'll be f of b. And that's picture 1. And then here's picture 2. So this is f of a. And again, this is f of b. Okay. So let's look carefully at the statement of this theorem. So suppose that f is continuous on the interval from a to b. So clearly the two graphs that I've drawn here, this function is continuous on the interval from a to b because you can draw it without lifting your pencil, and it's continuous from the right at a and continuous from the left at b. Same thing here. Definitely the graph of a continuous function here. And suppose that f of a is not equal to f of b. So that's true in both cases. Here, f of a and f of b are a little bit closer. And now we're saying let n be any number that's in between f of a and f of b. Okay, so I'm going to draw it. I'll draw it this way here. So here I'm going to pick one value for n, like this. And then here I'm going to pick another value for n. Okay. Notice I could not have picked n to be below f of a in this case because then it wouldn't have been in between these two. So now what the conclusion of the theorem says is that there's some number on the x-axis, so between a and b, where the function sends that number up to height n. Okay, so let's take a look at that. Okay, so here I'm going to draw height n, and here I'm going to draw height n. Okay, and now it's pretty easy to see. Okay, there's one possible number, there's another possible number, and there's another possible number. Okay, so any of these could be, C could be any of these. Any of these in this case, and here, well, C is that number. Okay, so take a look really closely. This is a subtle point. I apologize if you hear a little bit of stuff in the background. That's my cat, Shadowfax. Okay, fine, Shadowfax. Attention, attention. This is Shadowfax. He's the other cat. He's smaller than Sylvester. Whoa! He just kicked the camera with his tail. All right, get down. So Shadowfax was sleeping peacefully on the desk until just a minute ago. All right, back to the theorem. So we have we have a function that's continuous on the interval from a to b, and any number between it. Then there's a number between a and b that is that gets sent to the height n on the graph. Okay, so this is a very common sense notion. Okay, it's called the intermediate value theorem because n is the intermediate value between the two heights, f of a and f of b. All right, let's do a very, very quick calculation, and then we will be done with this section. So show that the equation (4x cubed minus 6x squared plus 3x minus 2 equals 0 has a root between x equals 1 and x equals 2. Okay. Now I don't know what the graph of this function looks like, but what this is asking us for is it's saying, okay, here's x equals 1, here's x equals 2. We just want to know that somewhere the graph of this polynomial passes through the x-axis. So there's a value of x between 1 and 2 where the function, this function 4x cubed minus 6x squared plus 3x minus 2 is equal to 0. Okay, so here's the solution to this. It's quite simple. So this function 4x cubed, we'll give it a name, f, 4x cubed minus 6x squared plus 3x minus 2 is a polynomial so it's continuous everywhere. It's continuous on all of our, but in particular, so it's continuous on the interval from 1 to 2. Okay, that's observation 1. Observation 2 is that, so f of 1 is equal to, well, let's see, we have to do a little bit of calculation. So if I plug a 1 in here, I get 4 minus 6, that's minus 2, minus another 2 is minus 4 plus 3. So minus 4 plus 3 is minus 1, right? And then if I plug 2 in here, let's see, so 4 times 8 is 32. Let's see, 4, I'm going to just do the math in my head. 2 cubed. I just don't trust myself. So this is equal to 4 times 8 is 32. This is 6 times 4, that's 24. This is 6, and this is 2. If the math comes out correctly, this is minus 26 and plus 38, so maybe 12. All right. So now, we look at this. So that means somewhere here at minus 1, the function will pass through height minus 1 at 1, and then up here at 12, the function will pass through height 12. Okay, but now notice, so that was part 3. Notice, so now minus 1, 0 is in between these two values. So this right here, this is the n in the statement of the theorem. So if we think carefully about the statement of the intermediate value theorem, it says if you've got a function that's continuous on an interval, and you pick any number in between f of the endpoints of the interval, then there's got to be some number. So this is part 4. Therefore, by the intermediate value theorem, there is a value, let's call it c. Okay, c will be in between 1 and 2, where f of c equals that intermediate value. Let me just check to make sure that you can see that on the... That's right. Okay, good. That's very good. That's all we needed to show. So we're going to stop there.